Okay, in this next problem we have a container with the shape of an open right circular cone as shown in the figure above. The height of the container is 10 centimeters and the diameter of the opening is also 10 centimeters. Water in the container is evaporating so that its depth h is changing at the constant rate of -3/10 centimeters per hour. So we write down that dH dt is equal to -3/10 centimeters per hour. And there we have the formula for the volume of a cone of height h and radius r. First thing we're asked for is to find the volume V of water in the container when h is 5. Well, we know that the formula for volume is 1/3 pi r squared h. And we know that h is 5, but we still don't know what the radius is. So with these types of cone problems, you very often have to set up a system of similar triangles. And if you do, you'll get the proportion that 5 is to 10 as r is to h, or that 10r is equal to 5h, so that r is a half of h. Now that's the way it is for the whole cone. The radius is 5 and the height is 10, and it happens to be directly proportional or proportional in that same way. So we can now plug in, we have pi over 3 r squared, which is 1/2 h quantity squared. Well, if we know that h is 5, then half of that will be 5/2, and then we'll multiply that by 5 for h. And simplified out, that would be 125 pi over 12, and the units would simply be centimeters cubed. And that gives us our answer for part A. Next, we want to find the rate of change of the volume of water in the container with respect to time when h is 5 centimeters. And so we're looking for dV dt. We want to find out what that is when h is 5. So we have a formula that relates dV dt and dH dt, and V is equal to 1/3 pi r squared h, but we already know that r is equal to 1/2 h. So we have pi over 3, 1/2 h quantity squared times h, which is pi over 12. We square that 1/2, h to the third power. And when we take the derivative of both of those sides with respect to t, we'll get dV dt is equal to 3 pi over 12 h squared dH dt, and we're trying to solve for dV dt, so we should be able to just plug everything in right now. So we have 3 pi over 12, h is 5, so we'll square that and that'll be 25. And dH dt is given to us as -3/10. And I can simplify that 3 over 12 to be 1/4. And that should simplify down to -75 pi over 40. And the units will be centimeters cubed per hour. And that does it for part B. Finally, in C, we want to show that the rate of change of the volume of water in the container, and that is just dV dt, is directly proportional to the exposed surface area of the water. The exposed surface area of the water is just the circle on top of the water surface, and so its area would be pi r squared. So to be directly proportional, y is proportional to x, we say y is equal to kx. dV dt is directly proportional to the exposed surface area of the water. We're going to say dV dt is equal to k times pi r squared. And that should be referring to the moment when the height is 5. So when the height is 5, the radius will be 5/2. And so we have -75 pi over 40 is equal to k times pi r squared. R is 5/2. R squared is 25 over 4. And all we're looking for is the constant of proportionality, so we multiply both sides by 4 over 25 pi, and we end up with k is equal to -75 pi over 40 times 4 over 25 pi, and we end up with simply -3/10 as the constant of proportionality. And that's a constant, so no need to worry about units here. And that does it for this problem.